Hello everyone, my name is Sentongo Joshua and I'll be presenting to you the knowledge distilled large acoustic model for emotion conditioned music generation in resource constrained settings. So let's get started. All right, so a brief background of this is we aim to develop an emotion aware music system for Uganda. Recommendations done by current systems that lack relevance to emotions and also culture. They use genre and artists instead, but people relate to music on a personal and emotional level. So the system we have created is aiming to bridge that gap. This is a workflow of the system development. So we got a data set, the dim data set, and then we expanded it as we shall see in later slides using our GAN system. Then we extracted the features that would have been the text features for the initial basic models, and then later the features from the spectrogram. And then we trained our models on either text features or spectrograms. For the vision transformers, we use the spectrograms, and then for the basic models, we use the text features. And then we continued on to training it and having results. So these are some of the related works that we found really helpful as we're making our research. Let me talk about the few that stand out. One is the music emotion recognition that uses convolutional LSTM. It is one that used a combination of both CNN and LSTM, convolutional neural network, together with a long short-term memory. It outperformed systems that just use CNN alone or LSTM alone. But one major flaw, one major limitation it had was it was risking overfitting of the data instead of actually learning or generalizing. Another one is the music in this motion by enemy. This one is the dim dataset, the same dataset that we also used for this project of ours, and they used the efficient net. One limitation it had was the complex pipeline that it possessed. It posed. Now, the problem statement here, the domain that we are dealing in is music, and as earlier said, people who are interested in music relate to it on an emotional level. Uh, and systems today lack emotional understanding because they are relying on just genre and artists, which are really basic features to base on to determine the emotional the music the music's makeup. Then we have models that are trained, but they are trained on generalized data sets they don't really capture the true emotional content. Now, the major limitation in this domain is the sparse emotional annotated data. So few data sets out there exist with most of them contain non-Western music with a few uh, African and local data sets. So there's a bit of imbalance there. And then the computational problem is large models that are able to do this kind of uh, emotional analysis, like the ones that have been already done from the related works seen earlier. They are so large that they consume a lot of resources and the processing power. That is the memory and the processing power. So uh, available data sets are too small to train a model. This is also a problem that we solved with the GAN system that I shall explain in more details in the coming slides. And also the latency time, the time taken for the model to receive an audio and then process it to get an output is also long, and yet people don't have the time to wait for that long. And we also adapt these systems to the cultural context. So these are our objectives, and we managed to achieve them. One was to identify the core features that can be used to relate to the emotions in a song, then generate synthetic data to overcome the problem of scarcity, then to create a large vision model, and then to distill that large vision model into a student model. These are the contributions and outputs. So we evaluated a pre-trained large vision model from Google. We trained it to with our audio spectrograms so that we align it to emotional analysis. Then we created a GAN that was to synthesize a new additional spectrograms in addition to the little that we had. And then we also created a feature importance framework, the one that we used for the text-based features to be able to tell which features were core necessary for learning. Now, this is the methodology and system. We have the GAN over here, the very first system that is working before the transformer gets the input. So we have training data that comes in to that contains the real samples, and then the GAN is fed on random noise, and it turns that random noise into fake generated samples, and then it passes both to a discriminator. The role of the discriminator here is to be able to identify what is real and what is fake. So it is a minimax game. The discriminator tries very much to be able to tell the difference between what was generated and what is in the original data set. And now it gives back feedback to the generator so that to tell it how well it did. So the two work together in this cycle, repeated cycle, until the entire system becomes so well that the discriminator is the generator is able to generate spectrograms that are close to the real thing. So it's more like generator creating counterfeit, discriminator trying to identify counterfeit, and then giving it feedback, generator becomes better. So then this combination of spectrograms is passed to this AST classifier, which breaks the spectrogram down into patches that are passed into a linear projector, linear projection, and then they're embedded and passed to further transformer layers. Then they're encoded, and out comes an output head that points to the valency and arousal values in that spectrogram, which is related to a song. Here is the distillation overview. So we have this teacher model. It is already trained, and it is transferring knowledge to the student. The student makes a prediction, passes that prediction to the teacher model. Teacher model gives the student feedback, telling it how well it did. Let's say the student model says that, oh, I have made an analysis of this song, and it is sad with this value of valency and with this value of arousal. Yes, the teacher model is able to tell it how good it performed. But in addition to that, it also says, well, you said it is sad, but actually it is 70% sad, 20% happy, and a 10% excitement. So now the student model not only learns to predict better, but also gets a pattern matching between these different emotions so that it can relate to them in its higher dimensional space where it does its computation. All right, so this is the system that an overview of how the system works. So we have incoming in the audio and then turned into spectrograms. They are passed to analysis model. Analysis model then does the analysis and returns the report to the user for the values of a valency, arousal, and an emotional label that is easily readable. So we also aim at connecting this analysis model to third-party systems, services such as Spotify, so that the system can actually do a prior analysis of those songs and then store the values in a database, such that if a user has a song similar to what we already have in the database, the system doesn't have to start from scratch. It can just return the value of values and arousal as well as an emotional label immediately. So this is the mathematical foundation for the GAN I talked about earlier. It's a minimax game. The GAN here is trying to minimize, and then the discriminator is trying to maximize. So the GAN has to be ensure that whenever it makes a prediction of something, whether it's to make a prediction of whether something is a real spectrogram or one that was already generated by the GAN, it has to be able to do that with a high level, with a high degree of accuracy. And the discriminator, sorry, the generator has to generate a model, has to generate a spectrogram that is indistinguishable from the real. Now, the discriminator, on the other hand, has to be able to determine that whether this is real or not. And there is this feedback that happens between the two, and the entire system becomes so good at generating spectrograms that are close to what is real. Now, this is the vision transformer. So in comes spectrograms. So our spectrograms have a height and a width in pixels. Height is 224 and width is 224 pixels. They also have channels, that is for the RGB, the red, blue, the green. So you can now have a picture of the spectrogram as a 3D entity. Now this 3D entity is broken down into patches of 16 by 16 pixels. So if you do the math, we can see that the number of patches are therefore summing up to 196. Now the patch dimensions are therefore obtained as the size of a patch times the channel size, which never changed. So the patch dimension is 768. Now these patch embeddings, they are turned into a patch embedding, which is a matrix where we get each patch dimension with its 768 integer values, and then we stack all of them. They are 196, so we stack all of them to get this two-dimensional matrix, and then we pass that two-dimensional matrix into a linear projection, which turns it into a one-dimensional matrix, a one-dimensional vector, which is then used by the transformer to make analysis. Then on the right here, we have the multi-head attention, self-attention. So each patch, if the transformer was to analyze the patch alone in isolation, then it wouldn't be able to pick up the patterns in the overall spectrogram. So the multi-head self-attention here is able to help the transformer connect the patterns in a certain patch with other closely related patches, so that it gets an overall picture of how the spectrogram of the features the spectrogram contains. So a brief description of the data set, as already said, we have those so many solitary songs, so we created more. So on the right here, we have a heat map, which has the reds or the maroons, depending on what you consider red and maroon. Then that represents high positive correlation. Then the blues represent the negative correlations coefficient. So we consider for the ones that use text features, we consider the high positive correlation coefficient, because those features were closely related to each other in such a way that they could provide a better mapping of the emotion value in a song. These were the outputs. I already talked about this earlier, yeah, showing that amount of spectrograms that we had increased from the initial to the 500 and plus that we came up with in the later parts. Now this is the model comparisons of all the models that we created: the ridge, the support vector, and the XGBoost. Those were initial models that used the text features. Then we had the CRN, AST, and the Google VIT. Those ones used spectrograms, and that was their performance. So this is the Google VIT that we pre-trained on our spectrograms. You can see that it actually did well. The CCC is so close to the original, so it follows this. It has a pattern that is closely following the right one. The CCC is aimed at measuring both the accuracy and precision, so it doesn't just focus on accuracy without the precision. So even if two are close to each other, but the values are so far apart, then it doesn't work out. These are the values of the AST, 0.71 for the valency, and then 0.78 for the arousal. And then the overall best was the Google VIT over here, which performed way better, and it had values of valency having 0.7 and then arousal 0.78, and it was the best model that performed the others. Here we have the expected results. The blues represent the ground truth, and then the reds here represent the predicted, and you can see there's this pattern that it follows. So I selected the Google VIT that the model shall deploy, and it deployed the model on render for the back end. Then we made a separate front end on Vercel, and the two communicate via fast APIs, and this is a general picture of how the system works overall. So user with their browser connect to Vercel, and Vercel makes API calls to render, sending the audio data. Then Vercel, the render server, makes analysis and returns back the results, which are displayed to the user. Grafana is there for monitoring. Our repos contain the project, which is then connected to the render accounts and the Vercel accounts. This is a demonstration of just the screens or the product. I also made a short video about that, 2-minute video. Now, one major limitation I would talk about the system is the knowledge distillation. Yes, because it is trying to transfer knowledge from a parent to a student, which is good because it reduces the size of the model and also makes it efficient. But then there's a bit of accuracy that is lost, but nothing too much to worry about. Conclusion, we picked the Google VIT as the final model, made a pipeline for transforming audio into spectrograms, which it can train on and then return results. And the next steps is to continue with this further to connect to the third-party services and also implement a diffusion-based model that can turn spectrograms into audio. I acknowledge the University of Geneva for providing us with the data set, and also Dr. Russell for his circumplex model, the one that uses valence and arousal. And also not forgetting our supervisor, Mr. Galiwango Marvin, for the good supervision. And I would like to thank you for the listening.